Speaker is Dr. Alexandria Volkening. She is an NSF Simons Fellow at Northwestern University, and she's going to kick us off with a talk on data-driven modeling. Take it away.
Thanks, Heather. All right, so I am excited to talk to you all today. Whoops, I'm also a little bit nervous, I think. I think data-driven modeling is a big topic. So what I'm going to do is give you an overview of some of the things I think about when I'm doing data-driven modeling and some of the things I think other folks might think about too. So it's going to be broad and hopefully give you some thoughts on things to think about in the future. But feel free to email me, ping me on Slack or over Discord if I say something that you want to learn more about a specific topic that I mentioned. So to get us started, I just wanted to set the stage for what we mean by complex systems. So when we say complex systems, what we mean is problems that involve individuals coming together to create some collective group dynamic that is bigger and more complex than the individual pieces. And so I think this is best explained by videos. I'm going to show you some movies. The first one is my personal favorite example of a complex system. This is an example of traffic jam forming. So before I start the video, what the setup is that there's a bunch of cars placed on a circular road. It's an experimental condition. There's no stoplights, no stop signs, and all the cars were placed equally at equidistant distances on this road. And so what you'd hope is that the cars just kind of smoothly move around the circle and that there's no traffic jam. But instead, what you see is that the cars actually do form a traffic jam. They've slowed down the video here, but you can see this kind of jam propagating backward relative to the direction that the cars are moving. And there's no one saying to the cars, form a traffic jam. Instead, this jam is kind of arising from the interactions of the individual drivers, how they react to the people in front of them, maybe how they react to the people behind them. And so then you get the traffic jam forming. And so one of my favorite things to do is to, either when I'm boarding an airplane or when I'm driving around town, is to think about how my kind of choices as I drive is influencing the larger traffic patterns. Now, another example of a complex system that might be one that we think about more naturally is flocking birds. So here you see some beautiful birds tracing out this pattern in the sky. And again, there's no one saying to form these kind of lovely patterns. It's coming from the individual interactions of the birds. Another example of a complex system is pedestrian movement. So if you watch this video, these people are just told to move through the corridor. So the folks in red shirts want to move to the left and the folks in black shirts want to move to the right. And you can see if we look at this, it kind of appears like there are stripes or lanes forming in the corridor and they break up and form again. And so there's no reason, no one is saying form lanes. Instead, it's just something that arises naturally from the interactions of these individuals. And then the complex system that I have worked on the most is one at a smaller scale. So I look at how patterns form on the skin of fish. And here you see a growing fish skin, and you might be able to make out these little black pigment cells that are moving on the growing skin and forming a stripe pattern on this fish skin. So again, from the interactions of these cells, you're getting a larger pattern. So this is, like I said, this is what I focused on the most. But today, what we're going to talk about is complex systems in social settings. But I think what's important is across all these different types of applications, it's some of the same mathematical tools they're used to study them. Okay, so in terms of complex social systems, there is a huge range of possible examples that we could consider. Just to point out a few, there are voter dynamics where we're interested in how do opinions change and how does that lead to various election results. On social media, we can think of echo chambers forming where people are kind of self-organizing with folks of the same ideology. Hopefully we have social media spread of our hashtags going on right now. And so we can look at how does the kind of the network dynamics lead to the spread of these hashtags. And so Heather and Daryl are going to talk more about networks tomorrow. Like I said, there's also things like pedestrian movement and airplane boarding. And so across all these applications, there are some of the same types of dynamics where, again, the kind of overarching feature is you have some rich group dynamic that is emerging from the interactions of individuals. And in the traffic example, like I said before, you can think of a car and the driver inside of it having some sort of sensing radius, how far it looks ahead of it to make choices based on it's going to slow up, slow down, or speed up. We have these various different Twitter accounts that are connected in different ways. There might be some, a few bots in the network also. And then we have pedestrians moving around and voters with different ideologies. So across these different systems, you can have things like agent alignment, where in some of these examples, it might be actually physically aligning with other agents and following others. In the ideology setting, it might be aligning with folks in terms of opinions. You can think of there being various different, so of course, everyone in these social settings is unique, but you can think of heterogeneity in the agents. So maybe in this example, drivers who are more or less cautious and how much space they want in front or behind them. And then you can also have changes in agent behavior. So maybe people adopt different opinions, or as a result to maybe unjust driving practices, they change how they prefer to drive as well. So we want to understand, how do we describe these features that are present across applications mathematically? And I think the general goal across all these systems, quite broadly, is either to understand how the agents are interacting normally, or understand how they might interact in altered settings. There are also cases where you just want to be able to predict the kind of group level features that result from the agent dynamics, and you're not necessarily interested in the mechanisms of how they're behaving. So the kind of questions we're looking at in this setting, right, might be what driving behaviors of the drivers are leading to traffic jam formation. We might want to design roads so that those behaviors are mitigated, or maybe put some autonomous vehicles into the system so that they can dissipate the traffic jams from forming. In these election dynamics settings, maybe what you want to do is just baseline question is understand, how do we forecast elections regardless of how the dynamics are kind of rolling out. We might also be interested in understanding how external events like media coverage are impacting people's opinions. And then again, in the echo chamber setting, maybe we want to understand what causes echo chambers to form, and how can we design things to help dissipate the divisions in these cases. So today, what I will do is going to have kind of two parts to my talk. I'm going to start by giving a very general overview of some of the approaches used in data-driven modeling. And I think if you get one thing out of this, this framework, well, two things. The first thing should be just that there are many different ways to do data-driven modeling. And the way you do it should be based on your question and your problem that you have in mind. And I think that across all of the examples that I'll show, really the thing that is in common across them all is just matching the complexity of your model to the complexity of the data in a reasonable way. So you're building models that are not overfit and that have the ability to predict interesting dynamics. So that will be the first part of my talk. It'll be broad themes across everything. And then the second part of my talk will be two more in-depth case studies, where I'll focus first on looking at different modeling perspectives on opinion dynamics in US elections. And then if there is time, I'll talk a little bit about pedestrian movement in corridors, where the point will be that this example uses quite similar ideas as the opinion dynamics problem, but it's more qualitative. And so that introduces, I think, more challenges in the modeling process. So these are the resources that I drew on when I was creating this lecture. And some of the ideas are directly from particularly this lecture here. I'll mention that all of these resources are freely available online. So they're great resources. We can post them to the short course website later so that you don't have to grab them right now. And of course, these slides are also available in the Slack. And then the book that I used was this book by Brunton and Kutz. And I'll point you to their YouTube channel because they have some nice lectures that they've recorded on YouTube as well, if you're interested more in their ideas behind data-driven modeling. All right, so let's get started by just setting the stage for what we mean by modeling in this short course and specifically today. And so here I've shown just a few examples of what people can mean by modeling in different fields. And so in biology, when I read papers related to this fish, they refer to this fish as a model or a model organism. And also in biology, you can think of schematics or kind of cartoons that illustrate different concepts that will be called models. And so this tripped me up for a little while when I was reading papers, because this is not necessarily my idea of a model, but a schematic or hypothesis can be a model. In statistics, it's common for a model to be some relationship between some inputs and some outputs where you know A, you know B, and you want to find X. And then from a mathematical perspective, when we think of models, we may think of network models like you'll hear about tomorrow, differential equations, stochastic rules, differential equations, a whole range of different things. And so I think in these two settings, what we're going to think about is a model being equations or rules that describe your system in a mathematical way. And I think the difference between the statistical models and the mathematical models is how you view parameters. So in a statistical approach, it's the equations and the rules plus the parameter values, right? The parameter values are really important. In the mathematical setting, I'm going to say that it's more the equations, the rules, and what are your parameters, just rather than the values they actually take on. Just what are we putting into the system? And then this definition of modeling is based on these various resources, but we're just thinking about modeling as being the process, and especially an iterative process, representing your system in a mathematical way so that you can either raise questions, make predictions, or better understand what's going on in the system. And so then there's a whole range of different qualities that a model can have. We can think of models as being deterministic or stochastic. A model can be time independent or time dependent. So when I talk about election dynamics, I'm going to show you one static election model and one dynamic election model. You can have a model that is spatial or non-spatial. So for example, in that crosswalk example that we talked about earlier with the pedestrians moving around, we could either be interested in just how many people are in the crosswalk, or maybe we actually want to know where they're located in the crosswalk. A model could be discrete or continuous. So you can think of discrete as just being the number of people in a room versus the density of people in the room. But discrete can also be something like an ideology either being Republican or Democratic, or it being some sort of spectrum between those two ideologies. So these are choices you have to make and simplifications you make as you're modeling. And then like we talked about before, models can be mathematical or statistical. And then another buzzword that you'll hear is models being described as phenomenological or mechanistic. So oftentimes people will think of mathematical models as being mechanistic, meaning that they are kind of getting at the mechanisms behind the agent interactions, and statistical models as being phenomenological and being slightly more black box. But I would argue that the distinction isn't that clear, and at least in my opinion, and I think it really depends on the perspective that you're looking at the system at. So just to give an aside related to this distinction, I wanted to mention two slides on fish patterns. So like I said, this is this application that I've spent a lot of time thinking about, where I'm interested in understanding how do the cells interact to form this fish pattern, and these are some simulations of models that my collaborators and I have developed. And so one of the things that's going into this model is that we know biologically that there are black cells and yellow cells, and that the black cells lead the way and the yellow cells follow them. So you can see this video of a black cell leading the way and a yellow cell following. So when I was building models, I took this and put it into a mathematical framework that I thought was pretty mechanistic, where you have a black cell being repelled and a yellow cell attracted to it. And then mathematically, all you're doing is just kind of prescribing a differential equation that is repulsive for this one and attractive for this one. So in some scale, this is getting at the mechanism behind the pattern, but the reality is all you have to do is go one step further into the application, and that is in and of itself a black box, because these cells aren't just being described, by ODEs, really there's much more complicated things going on biologically, where maybe there's signals diffusing, maybe they're reaching out legs to touch each other. So really, in some sense, what I thought was a mechanistic model was still a kind of black box phenomenological model as soon as you go to the next level of detail. So I think that this is an important thing to keep in mind across these systems, is that what the vocabulary means, and also just depends on the perspective that you're taking, and you can always build more detailed into your application. All right, so this slide is an overview of different ways of thinking about modeling and working with data in models that is based on this nice presentation by Humphreys, Levery, and Patelski, where what they do is think of models as living on a spectrum, where you have black box models being models that I'll say are models which just fit parameters, gray box models being models where maybe you fit the parameters, but maybe they're somewhat interpretable, and maybe you measure some of the parameters. And then white box models being models where all the parameters are fully measurable. You're looking at things like temperature, which you can immediately measure. And again, I think that it's important to keep in mind that this is a spectrum. It's not, none of these distinctions are clear cut. And in particular, as I'll show you a little bit later, some of the same approaches that are used to fit parameters for black box models are also used for gray box models. So they can depend on some of the same techniques. To give you some examples of systems that fit into these different types, you can think of machine learning and classifying images, for instance, different numbers, as living in the black box space. For gray box models, there's a whole spectrum. Some of these are more phenomenological or mechanistic, depending on your perspective. So one example would be describing how the cars are moving in this circle using an ODE, or an ordinary differential equation, per car. Another example is these are muscles that have arranged in patterns, and here they're showing that you can kind of replicate this pattern formation process using Cahn-Hilliard partial differential equations for the muscle density. So some of the parameters in these systems are related to muscle measurements. And then finally, the white box models would be models where we basically know what the equations are. We can pretty much measure all the parameters, things like fluid dynamics, Navier-Stokes equations. And so for the purposes of today, so that we can just put some kind of delimiters on what we mean by data-driven modeling, I'm going to be pretty broad and say that both of these types of models can fit into a data-driven modeling framework, both black box models and gray box models. And what I'll say for today, because again, this is, I think, there's many different definitions a person could have, but for today, data-driven modeling is going to be mathematical modeling that is heavily driven and based on data combined with specific knowledge of the problem and kind of surrounding a question or a goal that you have in mind. So that could be, for example, developing predictive mechanistic models in a mathematical sense based on data. It could be machine learning, regression, or classification based on data. And then I think one of the things that you hope comes out of either of these types of models is using the model to raise questions. So then you're actually turning it around and not just doing data-driven modeling, but using your model to drive data collection as well, and further questions, so that there's a feedback. Okay, so this is an example process that one might think about when they're building a data-driven model, where you start out, right, by just looking at your data and trying to determine what you want to build a model for. What is your broad motivation? What is your specific goal? I put answered, so questions to be answered in quotation marks, because I think that the reality is every model is wrong. So usually it's just a means of raising questions to go to the next level of detail and understand the system better. So we can answer and raise more questions, and in the process gain some understanding of what's going on. The next step I think is really important in data-driven modeling is to come up with a plan for building your model and evaluating your model. So this means keeping track of what assumptions you're making, assumptions on your data, assumptions on the types of dynamics in your model, and then determining which types of parameters you can get your hands on in a measured way versus which parameters you're going to need to fit. And so for those parameters that you need to fit, the key thing that I think ties, regardless of whether the models are statistical or mathematical, the thing that links them together is this need to, at the onset, break your data into sets so that you have a plan for fitting your model, testing your model, and then using your model for prediction. And then finally, once you've got this model in hand, right, you can validate your model using your test data. I'm not going to talk about this step, but this is something that one could do, is look at performing a sensitivity analysis or some bifurcation analysis to understand how does varying the parameters or varying the data impact your results. And then the key thing here, right, is to, at least all my models I think have always been wrong. So it's just figuring out how I'm wrong and then using it to iterate, to improve, and to build more understanding and keep going with this process. So some of the kind of challenges that a person might have when they're building models based on data, I think is first of all, some data is qualitative. And so then there's necessarily kind of subjective choices made in how you work with it. And some data is quantitative. A lot of data is quite messy. So I've done some election forecasting work, and I think that the hardest part was just getting the data into a framework that could be usable. It's important to keep in mind when data is biased or subjective. So Mason's going to talk a little bit about, well, a lot of it, about data ethics in about an hour. And then, you know, sometimes you have way more data than you know what to do with, and sometimes you have much less than you'd like to have. And I think one of the challenges specifically in complex social systems is a lot of times you're trying to build models to forecast events that are rare or that are outliers. And so as one example, this is a picture of each point here is the speed of cars versus the time of day. And so the key point is that early in the morning, the cars are fast. This is empirical data. And then kind of at rush hour, the speed of the cars drops down. We did kind of expect that. It pops back up. And then you have nice fast car movement for the rest of the day. But what you'll notice is there is some variability here. And so if you were to just kind of least squares fit this data, you might not be capturing all of this variability here, where these are kind of rare events where maybe there was an accident on the road. We don't know why this is emerging in the system. Another example that's some work with Heather and Joe, who are both involved in the course, is looking at tweets related to gun violence. So here we're showing you the number of tweets that were related to mass shootings as a function of time in January. And what you should ask about this data is, how did we determine what tweets were related to mass shootings? And that was a subjective choice. So I think that's just kind of being aware of where the subjective choices are in the data that you're showing, and being aware of what you can do to test the impact of those subjective choices. My video is, there we go. Okay, and then finally, this is an example of data that, sure, there's quantitative data here. We're going to know the speed of the people. We know the density of the people, but when we look at it qualitatively, we kind of see that stripes are forming, but it's a qualitative decision when the stripes form, how wide the stripes are. Those are all things that we are making subjective decisions on as we work with this type of data. So I think it's important to be aware of these types of features as you build your model from the onset. Okay, and then the other kind of issue with data-driven modeling, this is something that the statistical community describes with pictures like this, is that we're working with underdetermined systems that have an infinite number of possible solutions. So you have to come up with some criteria for what is a good solution. And in particular, in this example, the way you think about this is, if we wanted to understand how those people are moving in that corridor, if we asked the 289 people in this room, we could all come up with 289 models that would describe the behavior of these people in this corridor. And so again, what does a good model mean in this setting? There's way more unknowns here than we can get our hands on uniquely. And so the kind of general plan for dealing with this is to combine expertise in the particular application at hand, work with the specific goal that you have in mind, and be aware of your data to make a plan for model development and then model testing, balancing the number of assumptions you put into the model and the amount of data that you have, and then testing, I think, how uncertainty impacts uncertainty in your data, uncertainty in your parameters impacts your results. And so in terms of what good solution or good model means, what we're going to say is a good model is one that is as simple as is useful, describes your system, and is both developed based on data and then tested on separate data. Okay, so I can give you a little example of how this works out in practice, but this is an example based on polling data. So suppose you were given some polls leading up to an election, and you were asked to forecast what the result was going to be the next day. So looking at this picture, this is data from Huffington Post, where we have the percentage of voters who say they're going to vote Democratic in Nevada versus the number of days before the 2012 presidential election. And so each green point here is one poll. So the first thing you should think about when you see this data, or one thing that you can think about when you see this data, is it's quite variable, it's quite messy. If I were to look at this data, I wouldn't know what was going to happen. And maybe there's time dependence here, it's kind of unclear. So one possible option for coming up with a forecast for this data is just to say, I don't think there's any time dependence. I think that these polls are just snapshots of people's opinions, and the kind of what's going on externally doesn't impact it. So you could just take the mean or a weighted mean of the polls and come up with some static forecast and take that mean as your forecast for the next day. That's one option for building a model based on this data. Another option would be to say, no, I think that is really every single glip in that polling data is important and captures some dynamics that are at work in the system. And so you could, in theory, fit some polynomial curve that goes through every single data point in this picture, right? And so if you were to do that, you would have zero error between your model and your data points. But at the same time, all you need to do is run this curve one single day more, and it would just blow up, right? It's probably not going to be able to predict things in a meaningful way, because really what it's doing is capturing some noise in the system. So you can think about this using this. I like to keep this quote in mind, right? But this is the idea that if you have a bunch of free parameters, you can do anything. There's not a question, right? I think I heard oh, good. Okay, I'll pause for questions soon. So point being, with a bunch of free parameters, you can do anything. You can fit a curve that goes through absolutely everything. But really what you want to balance is these two extremes. So in this case, what you're doing is there is a lot of error between the purple line, our forecast, and the green points. So maybe in this case, you've chosen a model that is so simple that it's not quite consistent with the dynamics. And so then if you think of this curve here, where this is the error between your model and your data, it's going to be bounded below by some value. You're not going to be able to improve it. Regardless, you try all sorts of lines, but you're not going to get much better. And then in this case, you have fit your curve so carefully to the data that here your model is so complex that you have zero error between your green points and your purple curve. But as soon as you try to make a prediction or a forecast with your model, you test it on your testing data set, then the error is just going to increase significantly. And so the key is to do something in between, where you are balancing the number of assumptions that you put into your model and the amount of data that you have available, or you're balancing how good of a fit you have on your testing data set and how much predictive value your model has. All right. And so breaking up your data into a set for testing and for development of your model can look different based on different applications. And so this is why you need to have some domain expertise for the problem to select this and to break test sets and model development sets in a reasonable way. But to give one example, so this is what Heather and Joe and Sarah Eames and I are thinking about doing for this Twitter data set. We have this set of tweets related to mass shootings over the course of a year. And our kind of general plan is that we are going to build a model based on the first half of the data. We're locking the second half of the year in a lockbox, not looking at it. And then we will test our model on the second half of the year and see whether it's good or not. At that point, we'll probably have to redefine what we mean by mass shootings and try it again and see if it depends heavily on our definition of mass shooting. So this is one way of doing it with quantitative data that looks like this. But you can also do this in problems that rely on more qualitative data. And again, it very much depends on the application at hand. So my work has largely been in fish patterns, like I said. And for this, the type of data I'm working with is some measurements of cell speed and stripe width, but really I'm working with a bunch of fish pictures. And so what we do is use the fact that you can break these fish pictures up into different types, and we fit them to fish pictures that basically involve, I'm not going to go into the biology, but they involve setting parameters in the model equal to 0. And we know it involves setting parameters into the model equal to 0. So you determine what your model should be based on the red set of fish. And once you have a model, you then basically simplify it by hand by trying to, are there any more parameters that you can set to 0? Is there anything you can do to make your model rules simpler? And so this is kind of an iterative process. Once you think you're as simple as you can be, then you test the model on some other experiments. These are experiments where you know exactly how you should change the parameters to reproduce them. That's this gray set. And then finally, you can use the model to predict things where you have no idea how you should change the parameters. And your goal is to use the model to say, this is how these parameters change to create these fish. So this is an example where it makes sense to have a set of data for fitting, testing, and prediction. In the last example I showed you, it was really a set of data for fitting and then a set of data for testing. Okay, so I think I will pause there before I jump into looking at some more examples in detail. Are there any clarifying questions at this point, Heather? Okay.
So this question had a bit of discussion in the chat, but I think it's worth passing on to you as well. This is from Stephen. Is mechanistic understood to be causal?
So that is, I think that's probably a buzzword that means different things to different people also. I'd say, I think mechanistic is meant to be what is the actual, not just describing what's going on, but what is the mechanism behind it that's driving it. So in that sense, yes, I'd say it's causal. And so in this particular example, right, by just saying the black cell moves away and the yellow cell follows it, I'm just describing what's going on, but I'm not saying what determined that, what you could say what caused the black cell to move away and the yellow cell to follow. Yeah, so I think causal is reasonable.
All right, so we have another question from Anchita, and she is asking about the example that you gave about phenomenological versus mechanistic perspectives. And is the former really just the latter underneath if you break it down enough?
That's a good question, Anchita. I've also seen your work on Twitter, so it's nice to meet you virtually. Yeah, so I think the questions about phenomenological and mechanistic are really good, because the reality is I think this is the of this list of terms that I gave, it is the one that is the most kind of subject to interpretation. So don't take what I say on this to be ground truth. This is just one person's opinion. And the reality is, as someone who builds models that look like this, I, up until I'd say last year, always thought of my models as mechanistic. And it wasn't until I talked to more biologists and to more biological, mathematical biologists than myself that I realized that that community views them as phenomenological. So in some sense, yes, you can think of it as it's really just like a stepping stone behind every, I mean, each mechanistic model is in some sense a phenomenological model as soon as you step down to the next scale of the application.
Great. Okay, let's do another one from Rachel. This is great for people coming from different communities. So would the training, test, and predicting sets that you're talking about in this context also correspond to the training, validation, and test sets that you see in machine learning?
Yeah, so I think it just comes down to the vocabulary words that you use, absolutely. So let's see. Let me see what I can show. So I call them model development. So what should the rules be? And model testing sets. But the exact similarity in a machine learning would be model training versus model evaluation or model testing. You've got it.
All right, we'll do one more midpoint question, and this comes from Rebecca. So she listened to a statistics talk about how if you collect data, and even if it's not completely random, you might have some problems with your sample size. So how do we collect data in a way to avoid bias?
That is it.
That's a hard one.
That's a good question. I don't know if it's a fully solved question. I think, I mean, I think in some sense, it's hard not to collect data without bias, but it's important to know as much as possible what the bias you are introducing into it is. I think I'd say that. But maybe that's something we talk more about in the Slack channel as well, because I think that's a really interesting question. And maybe Mason will talk about more about data collection as well in his lecture.
Sounds good. All right, let's move on. We'll have another chance for questions at the end too, I think.
That's right. Okay. So the next thing that I'm going to do is jump more into a specific application. So probably it'll only be opinion dynamics that I talk about, but you can look more at pedestrian movement if you'd like, because I said the slides are on Slack. So let's think about different perspectives for understanding opinion dynamics during US elections. And let's go for it. All right. So the general question here to start with could be, for example, we want to understand election forecasting and be able to determine who is going to win an upcoming election. And so I like to think of opinion dynamics as a complex system because the resulting election dynamic or result of the election is coming from the interactions of individuals. They're driving the result. And so what you see in these two pictures is two examples of the forecasts of the electoral votes going to Biden and Trump from 538 and The Economist, right? And so for both of these systems, their general goal is just to forecast elections. They don't necessarily have as much interest in how people are changing their opinions and why they're changing their opinions. They want to understand phenomenologically what's the result. And the types of data that they're building into their models are things like how have states voted historically, what are the approval ratings for the current president, how is the economy doing, is the president incumbent or not, and polls. And so I'm going to differentiate between approval ratings and polls as being different things, even though approval ratings are also polls. But for polls, that's really just going to be who are you going to vote for in November. And so the first thing to keep in mind related to some of these questions is what are the issues with each of these data sets? What should we be aware of? So for example, with historical data, here you're showing various votes versus approval ratings for different years. The issue with historical data is, states are changing in time, opinions are changing in time. So just because a state historically voted one way doesn't mean it's going to vote that same way again. So it may not be representative. And then for the polling data, getting a representative sample is challenging related to that question earlier. And the other issue just to keep in mind is when we're working with polling data, say if you go to 538's website and download their publicly available polling data, which they do a really nice job of making available, that is not raw polling data. That is polling data that has been collected and then some polling organization or house has made some decisions about what they think a likely voter is. They've weighted it based on the demographics that they think are going to vote. They've weighted it on whether the people who they called usually have voted in the past. And the issue is that usually the way they weight that polling data is proprietary. So we're all working with data that has been adjusted in some way, and we don't know how it's been adjusted. The other big issue is that when you look at kind of trajectories like this, one of the challenges is, are these kind of little shakes in the data real, in the sense that something happened externally that forced people to change their opinion slightly, or is this just glitches and kind of error in how the polls were collected? So those are some of the challenges to be aware of when working with this data, even before you build a model. So the first kind of approach to building an election forecasting model that I want to highlight is a statistical one. So this is from Allen and Bromowitz. It's the time for change model. This is related to some of the models that The Economist uses. And so this is a deterministic, static, very much phenomenological model from a statistical perspective, where what they do is say the percentage of the vote that the incumbent is going to receive is just some parameter plus some other parameter times the current approval ratings in June, plus some other parameter times how the economy is doing, so the GDP growth rate, plus some other parameter times whether or not the current candidate's party has been in office for a while or not. And so the general approach then is to set up some system that looks like AX equals B, where as you go down these columns, you're just looking at the presidential approval ratings in 1972, 1974, 1976, 1978, and so on, right? So it's just time down these columns. And then what you're interested in doing is using that historical data to determine what your weightings should be. And so what Abramowitz does is just do a linear regression to identify those parameters, get some parameters out, and then he pops in the approval, GDP, and incumbency values for the upcoming election, and that is his forecast. So the benefit of this type of phenomenological, statistical, static approach is that it's quite simple, right? It also gives us the opportunity to make forecasts very early, where you can you don't have to wait for polling data to be available, and it's not dependent on that polling data, which we said already has issues associated with it. The drawback is that it's heavily reliant on the idea that the past is going to be the future. It's also not dynamic in any way, so we can't test how external events are impacting things. And it doesn't tell us anything about the mechanisms behind which people are actually forming their opinions. And kind of another kind of approach that would be related to this is you could ask, how did Abramowitz decide that the terms he should use are approval, GDP, and incumbency? It's a good question. So what a person can do, and I would encourage you to read about this on the Economist website because they have a nice description of this, is you can instead build a model where you look at more terms. So here, these black columns are some other historical data that you've collected. And you can ask, well, maybe that historical data is important as well for forecasting elections. And so then you are solving for what your parameters X should be by minimizing some error. And here, what I'm showing is instead of just minimizing the least squares error between AX and B, which is this term here, you can introduce regularization terms. So that's this lambda 1 times the absolute, the L1 norm of X, and lambda 2 times the L2 norm of your parameters. Where by tuning lambda 1 and lambda 2, what you're basically doing, especially in this case, is selecting models that are sparse. So that's a word that just means models that have a lot of zero terms. So you're kind of asking, how many features should I include in this data? What terms should I set to 0? And so the way The Economist uses this model is they actually use something called elastic net regularization, where they set both lambda 1 and lambda 2 greater than 0, and they're interested in understanding what terms should be in their statistical model. And so once you have some model, this is related to one of the questions that was asked earlier from a statistical perspective, what are some methods for validating the model? And so here I'm highlighting 2, they are related. So if they look similar, it's because they are similar. So in k-fold cross-validation, what this means is that you take your data. So for example, you take your historical election results, and you just break it up into a training set and a test set. And then the idea is within your training set, you take some random sample of the training set, fit your model to that, get some parameters out. And you repeat that process k times just with that training set. And then at some point you say your parameters are, say, the mean across all of those parameters. And then you can test it on your test set. So k-fold cross-validation is one approach. Another approach, which the economist uses, is called leave p out cross-validation. So here the difference is that you take all of your data together and you pull out a couple pieces of data, train on all the data left, test on the data that was withheld, plop it back in, and then you take your data again, pull out some other data, train on what's left, test on what was pulled out, plop it back in, and you keep pulling out different portions of your data until you have trained on all of your data and tested on all of your data. Now, I think really all this amounts to is just different methods for making sure that you break your data into sets for model development and sets for testing or prediction. So that's kind of the overarching feature of this. Okay, so that was a statistical approach to election forecasting. What if we want to move towards more of a mechanistic approach, where we have a little bit more understanding of how the opinions are changing in order to lead to some election result? So this is some work that I've been doing with Mason and Daniel Linder and Greg Rimpala, where what we were interested in doing was, from our perspectives, we just wanted to understand election forecasting better and understand it a little bit better from a mechanistic perspective. And so what motivated us was, in part, pictures that look like this. So this is from 538, but it's an image that shows that while elections are decided within each state, your error in your forecast is correlated in states that have similar demographics in common. So basically all we're saying here is that oftentimes Wisconsin and Minnesota, because they're kind of similar states, vote in a similar way. And so Wisconsin is going to be more likely to vote like Minnesota than it is going to be to vote like California, for example. And so we were interested in understanding what are these relationships between states. This correlation table is symmetric, right? Wisconsin is related to Minnesota, just like Minnesota is related to Wisconsin, but we specifically were interested in understanding, is it possible for voters in different states to influence each other? And so this is the major feature that we wanted to build into our model, where we didn't just want to forecast elections, we wanted to start to understand a mechanistic perspective on this. And as you'll see, I think another major goal of our work was not to answer the question of election forecasting, but really to start to raise questions for future research in this area. So the approach that we used to develop a model for forecasting elections in a towards mechanistic way was to build a model on the susceptible, infected, susceptible compartmental model, which we all are probably more familiar with now than we wanted to be a year ago. So this is a model that is commonly used to study biological diseases, where what you do is break your community up into two groups. People can be susceptible to a contagion or infected with a contagion. And then there are two dynamics in the system. Susceptible folks can become infected, and that depends on some transmission parameter beta when susceptible and infected individuals interact. And then infected individuals can recover, and that depends on some parameter gamma. So if you assume that your system is nicely mixed and everyone is interacting equally likely with everyone else, then you get the system of differential equations here for the evolution of the number of susceptible and number of infected people in your community. So we wanted to just take this kind of general model and reframe it as a way of forecasting elections. And so if you want to do that, the first thing you need to do is, if you want to be nonpartisan about it, right, you have to recognize that there are not just one disease propagating during an election year, there are at least two. So we reframe it to say someone can be infected Democratic or infected Republican, right, where of course the terms don't completely apply. And then susceptible individual is just someone who is undecided or some other type of voter. And so then what we're looking at also is just indices. So we want to understand the number of Republicans undecided voters and Democrat voters in state J in order to forecast the results. So this is the system of equations that we came up with then. It's very closely related to that original susceptible, infected, susceptible model I showed you, where here we're just saying that the evolution of Democratic voters in state I depends on demographic turnover. This is like recovery in the disease setting based on some parameter gamma. And the sum of the interactions between voters, Democratic voters in state J, their influence on undecided voters in state I. And this depends on some parameter beta IJD, which is capturing the influence of Democrats in state J on undecided voters in state I. And then similarly, there are other parameters in the Republican system as well. And so what we did to fit parameters to this model is actually quite similar to the way the parameters were fit in the statistical approach I showed you earlier, is we were interested in fitting parameters by matching these equations, the ordinary differential equation versions of these equations, to timelines of polling data. And so it looked like this, where we took all that green polling data that I showed you earlier, we binned it in 30-day increments. That was a subjective choice to get these purple asterisks that were the means of the polling data in each bin, and then we fit our equations to the data, just using a nonlinear least squares fit. And so our model is quite simple in the sense that we didn't do much anything to the polling data we work with. This is a difference from forecasters like 538. I'm not going to talk about the simplifications we made, but it's just important to keep them in mind. And so the result of this is that we were able to forecast elections, just as well as some of these other approaches. And it's moving towards a more mechanistic understanding of what's going on, where we have these differential equations, and we can now introduce, for instance, time-dependent external events into them and understand how the relationships between states are changing in time. And so I'm going to shout out to my student Will, who is going to talk about this at the joint math meeting later this week, if you're interested in knowing more about this in particular. Okay, so the final thing I think I'll talk about, pretty much the final thing I'll talk about today, is another approach to forecasting elections would be to instead kind of combine ideas from both the statistical community and the modeling community and use something called sparse identification of nonlinear dynamics. And you can see the references for this idea here. But the idea is, instead of specifying that the model is a disease model and specifying the exact form of it, instead what you do is use your data to discover what the equation should be from the data. So this is an example of what the system might look like, where you here D1 is just the polling data for state 1, and this is it's polling data in time. R1 is the polling data in time for Republicans in state 1. D1 squared would be just squaring the polling data in time for Democrats in state time. So this is a matrix that is constructed based on the data. And then over here, you can estimate from your data what is the change in the percentage of Democratic voters in time for a given year, the change of Republican voters in time for a given year, and so on. And so you can set this up as a linear regression problem where you let the data determine what terms you should have in your equation, and then what you're really after is these parameters, where you're hoping that many of these parameters are 0 in this setting. And so these parameters are often called loadings in this community. And so that's another way of determining a model based on data, where here, because you're introducing a huge range of possible models, you have to introduce what is a good model. And so it gets back to the original point, which is that if you're considering all these possible models, you want to pick one that is as simple as possible. The statistical community will use different metrics to decide what is simple or what is best, but all this comes down to is balancing the complexity of your model and the complexity of your data in a useful way. Okay, so the only thing I will say on pedestrian dynamics is just that I think if we look at other types of problems, so problems that are much more qualitative, that are not given some trajectory of quantitative data that we can fit to, you can do the same kind of thing where you fit your model to data and you search across parameters to reproduce qualitative features in your system. It's just that you have to be aware of how you measure those qualitative features in a useful way. I think I will stop here. If people have questions about working with pedestrian dynamics, I can talk about it in the chat or in the 30-minute break. But what I will leave you with is some of these quotes, just to keep in mind, right, that there are many different ways of modeling complex systems. We want to start as simple as we can, be very careful to break your data into sets for training or development and testing or evaluating, and balancing the number of assumptions you put into your model with the amount of data that you have. And then I think the key thing is to be comfortable with being wrong, because all these models are wrong, but hopefully we are iterating towards useful models in time. So I will go ahead and stop there, and thank you all.
All right, let's thank Dr. Volkening for her wonderful talk. You can visually clap. You could use the reactions to show your support for her talk. Thanks so much. We have time for just a few questions, but I promise I have collected them all, and I will pass them on to Dr. Volkening. So anything that doesn't get addressed, especially some of the more specific stuff, we'll pass that on, and then that's something we can discuss in the Slack. So the first question I have for you comes from Emma, and she asks, if you have a mechanistic model and a phenomenological model that perform approximately as well, is it reasonable to choose the mechanistic one?
Oh, that's a great question. I think that it depends on, so it's all about building your model to the level of data that is known. So, and the level of data that you know. Let me see. So for example, in this system, because I know the most about this system, I think in this setting, when I was initially building these models, all we knew was that black cells are repelled and yellow cells chase. If I had built a model that said black cells have a diffusing signal that spreads out from them, and when the density is greater than 32 with some units, then the yellow cell moves away. If there was no biological data on that being the case, that would just be me throwing a bunch of guesses and assumptions into the system. So I think it's not necessarily that a phenomenological model and a mechanistic model, one is better than the other. It's more about picking the one that matches the amount of data that is known. Because if you're building a mechanistic model without any kind of detailed knowledge of what's going on, then you're just throwing assumptions into the system.
All right, great, thank you. Our next question comes from an anonymous commenter, and they were wondering if you could briefly discuss how PCA or bootstrapping fit in with your discussion of modeling alternatives.
Okay, so I think, so I can send some resources on that if this person pings me on Slack. I'd say it's certainly important to do various different types of data analysis when you're maybe even before you start the modeling process. So something like principal component analysis could come in and understanding, for example, let's see. Oh, it's not letting me escape. So let me see, is my screen still shared?
No. Oh, okay. There you go. Yep.
So for example, in some of these systems, I think what could be interesting would be, so when we looked at this video here, since the people are wearing red shirts and black shirts, I think it's easy to say there are two types of people in this video, red shirt wearing people and black shirt wearing people. But what might be interesting would be to understand, looking at the trajectories of their positions and the data on their velocities, could you cluster it into more groups? Should there be more than two groups here? Maybe some of these people are pushier people and some of them are more cautious. So I think some of that data analysis tools can come in to help you identify what your modeling choices should be ahead of time.
All right, it looks like, thank you so much. This was a really wonderful talk. I feel like I learned a lot. I hope you all learned a lot as well. We'll pass on the rest of the questions to Dr. Volkening. And otherwise, I hope you will take a quick refreshing break and join us back in about 30 minutes for our next talk, which is going to be on data ethics. And I think it's going to be a great follow-up to this one. So thanks all. See you soon.